What if we could filter CO2 out of nitrogen using just a carbon-based material? In this Chem paper, we investigated exactly that, showing how Grazyne membranes can harvest CO2 from nitrogen with high selectivity and low energy cost. My name is Adrià Calzada, and today I will walk you through a quick summary of our findings. But first, why is this separation so important? As we all know, CO2 is one of the main greenhouse gases. It's present in the atmosphere mainly due to industrial emissions, and is a major contributor to climate change. In the air around us, nitrogen makes up about 78%, while CO2 accounts for just 0.04%. Despite these very different concentrations, both gases play key roles in industry. For example, nitrogen is used in the production of ammonia, and CO2 is essential for things like carbonated drinks. Now, separating them might sound simple, but in reality, both molecules are chemically very stable, and that makes selective separation much more complex than it seems. To tackle this challenge, we propose the use of grazynes. But what are grazynes? Grazynes are 2D carbon-based materials made by combining graphene stripes with acetylenic linkages. Their main advantage? They are highly tunable. That means we can create pores with very specific sizes. So, for example, we can design pores with the right dimensions to let certain molecules pass through, while blocking others. Although our study is entirely computational, there are synthetic routes that have been proposed, suggesting that grazynes could be synthesized in the near future. So, can we actually separate CO2 from nitrogen using grazynes? To explore this question, we designed two types of grazynes. Let's call them A and B. Both have the same pore size, but there's a key structural difference. Grazyne B contains two consecutive acetylenic stripes, while grazyne A does not. This small variation can lead to significant differences in how gases interact with the membrane. So now, let's jump into the results. Based on our DFT calculations, we found that CO2 is more likely to cross the membrane than nitrogen. This trend is supported by the rate constants. CO2 diffuses faster and appears to pass through in a shorter timescale. When looking at the selectivity, both membranes clearly favor CO2, especially at lower temperatures. In fact, the selectivity is some order of magnitude higher for carbon dioxide compared to nitrogen, which is a very promising result. On the other hand, our molecular dynamic simulations confirm these trends. In this image, we show the number of molecules crossing the B-type grazyne. As you can see, CO2 consistently reaches the permeated site in higher numbers across all pressures tested. From these simulations, we also computed the permeability, and again, carbon dioxide showed a significantly higher value than nitrogen. This consistency between DFT and molecular dynamics strengthens the conclusion that grazynes enable selective CO2 transport. If now we compare the two membranes, it seems that grazyne B behaves more restrictively. Its permeability is lower for both gases. However, the difference between CO2 and nitrogen permeability remains substantial, meaning that the separation is still feasible even with the more restrictive structure. And here you can see the filtration process in action. Carbon dioxide molecules successfully crossing the grazyne A membrane. These dynamic simulations give us a visual confirmation of what the calculations were already suggesting. Selective carbon dioxide separation with grazynes is not only theoretically possible, it can be realistically modeled and potentially applied. This work was supported by the Spanish research agency, the María de Maeztu Unit of Excellence, AGAUR, and ICREA. And thanks for watching this short summary.